Tuesday at class time, 1 o'clock at the latest. I might try to get it posted this weekend. What it's going to be is that it'll be, of course, online, and you'll have a period of time to take the test. Now, the test will be timed, and the length of time for the test will be the length of, say, a regular class period, what that would be. That's about an hour and 15 minutes. Now, what that means is for this test, even though you're taking it at home, and you might say, well, how difficult is this going to be? I just have my notes and everything, shouldn't be too bad. Well, here's the thing. The thing with online tests or any kind of test is if you haven't studied for it, by the time you take it, you're going to be much slower at it. You're not going to recognize certain symbols. You're not going to remember certain techniques, and you can eat up a lot of time looking things up. It's a technique called cookbooking, when you cookbook a test. Oh, here, let me adjust the camera. It looks like my head's getting cut off a little bit. You want to avoid cookbooking a test because it takes a lot of time to cookbook things. So what ideally you want to do is be familiar with the material before taking the test. It'll make it faster, more efficient, you won't run out of time, and honestly, it gives you more confidence. So I definitely recommend, even though it's going to be done at home, prepare for the test as best as you can. What's the best way to prepare? Well, I'm going to do a review today, and the review is just sort of reminding us of certain topics, maybe going over a few tricky ones, like we'll look at scientific notation, we'll review scientific notation, how to put something in scientific notation, how to take it out if it's a big number, how to put it in the scientific notation, how to take it out if you're dealing with a small number. We'll review things like that. But it's mostly just a review. It's just to kind of look at things and like, oh yeah, there's that. What you really want to do is you want to practice problems. I'll give you an example of what I'm getting at. When I was in school, I had a differential equations class, and I had a final exam coming up. So what I did is I listed the different types of problems that would be on that test. And I did every type of problem. I did 3 problems. So if it was, say, golly, I had to do something with a series solution. Well, I did 3 problems that involved series solutions. So, and then if I had another problem that was more sort of a simple moving variables around, then I would do 3 problems where I'm moving variables around. I did this for each of the types of problems that I figured could be on this test. And by the time I took the test, the final exam, I did fine. It wasn't that bad. What did it was practicing the problems. And I highly recommend that to anyone, definitely with mathematics. So practice problems, that's what I recommend. Second thing I'm going to recommend, when you take the test, you want to start with the easier problems first, and then go to the medium problems, and then the hard problems. Now, why do I recommend this? Now, there might be arguments not to do this. I'm going to argue in its favor, and this is why I think it's the favor is on this side, or this isn't a bad strategy, is you have points. These problems are worth points. You want to earn as many points as you can. And if you do the easy problems fairly quickly or relatively quickly, or maybe one takes a long time, but you know you're going to get it right, get those points. And then easy is kind of relative. Like you might think scientific notation's easy, but you find graphing really hard. But somebody else likes graphing, but just scientific notation, yikes. So it's kind of relative. What you want to avoid is a situation where you have a really hard problem that really stumps you. That's fine. It's fun to work on hard problems. Don't get me wrong. We want hard problems to solve. But you gotta watch the clock. You don't want to spend so much time on a hard problem that it eats up all the time, and then you don't have time to get to the other problems, let alone get all those easy points with the easy problems. So you want to be careful of time. So that's why I recommend do the easy problems first, easy for you, and then go for the trickier problems last. That's just my recommendation. The last thing I'm going to mention is if you're going to study, start studying soon. I'd say start studying right now, like tonight, Friday. The test, if I post it, say, like on a Friday night, try to get some study in before Friday night. And if you're going to be doing the test on Tuesday, if I post it on Tuesday, try to get your studying done over the weekend. I'll be honest, I save my studying a lot of times for the night before. It's mostly Word, but you can do yourself a huge favor if any work you could do beforehand. Also, you never know what's going to happen the night before. You might get called into work. There might be an emergency. There's a lot of things that could come up that could prevent you from studying for the test. So you want to make sure that you try to get as much studying in as you can before that test appears. So those are sort of my 3 things. Practice, practice, practice. I recommend starting with the easy problems and then going to the hard problems when you're taking the test. And then try to get a head start studying. And at the very least, if it's not because, let's say you don't get called into work, it's going to make studying the night before much easier. And that always helps. That can help. So those are the 3 tips I have for the test. So now I'm going to get into the review. If you have any questions, again, let me know. And I'm just going to kind of start going over things. I'm going to probably go over more calculation type stuff. Like, for example, in section 1.1, page 2, you've got the vocabulary. So I'm going to recommend going over that on your own for now. I'm going to look at some more computational type stuff. Like, for example, how to evaluate an expression. So this is a simple expression, not a very difficult one. Here, let's make it a little harder. Put a square in there. So when we evaluate an expression, one thing with an expression is we don't have, this is the expression, and it doesn't have an equal sign. So what we're going to do by letting x be equal to 2, and just the x is equal to 2, the expression is just by itself. It still doesn't have an equal sign. We're going to replace x with 2. And now we want to follow our order of operations. So that means we want to do exponents first. So 2 squared is 2 times 2. This will be 6 times 4 minus 7. And again, you want to think about order of operations. Order of operations means we do parentheses first, then we do exponents, and then we do multiplication and division, and they're actually kind of on the same level. We don't choose one over the other. I'm just checking if I got it okay. The way we handle multiplication and division is we look at our expression, we start on the far left, and we do these computations until we get to the far right. Lastly, we do addition and subtraction. And again, starting from the far left and just computing additions and subtractions as we go, maybe subtractions and additions that could be all mixed together, but we do these little calculations going left to right as well. So multiplication versus subtraction. Well, multiplication and division come first. So we'll get 24 minus 7, or this will be 17. So any questions about that? Again, this is just finding the value of an algebraic expression. Now, something else that did come up. exponents. Just like multiplication really means repeated addition, like 5 times 3 is 5 plus 5 plus 5. 7 times 3 is 7 plus 7 plus 7. Exponents are the same way. 5 to the third is 5 times 5 times 5. 1/2 to the third would be 1/2 times 1/2 times 1/2. With negatives, you got to be careful with these. And this is what I mean. If you have, say, -2 squared. Now let's go -3 squared. Well, what this means is -3 times -3, which is equal to 9. Now, where things can get different is if we have this, -3 with no parentheses. What this really means is this. Because following order of operations, we're going to square the 3. This negative can be thought of, this might be a better way of putting it, is -1 times 3 squared like that. So when we have this situation, we're not thinking like this. We got this situation, we're thinking like this. Yikes. And so this would be -1 times 9, or -9. So you want to be careful. If there's no parentheses, order of operations is going to tell us to apply this first and only to the number, leaving out the negative sign to the very end. So you've got to be kind of careful with that with exponents. So integers or types of numbers. There's the natural numbers. These are numbers we count on our fingers. There's whole numbers. The only difference here, there's a 0. Integers. These are the whole numbers, but with negative numbers included. So those are your integers. Rational numbers. These are all fractions. Now, we can't let b be 0 because we don't want division by 0. But examples of these, well, the number 3. Why the number 3? Well, you can write it as 3/1. There's A, there's B. Okay, more familiar things like 1/2, -3/2, 1/3. But those are examples of rational numbers. And the way you think of rational is think ratio. You know, one number over another, a ratio. And that's where we think of rational numbers. Now, the next type, a little more tricky. Irrational, or no ratio. These are numbers that exist. They're actual numbers, but they can't be represented by a fraction. So the number 1/3, well, that's not irrational because, well, even though it's 0.33333, oh, the threes go on forever. They repeat forever. You can take 0.3 repeating and represent it as a fraction, 1/3 or 1/3. These are going to be numbers that have decimals that go on forever, but you can't represent them as a fraction. We represent them using symbols. So pi and it goes on forever. E, and it goes on forever. Square root of 2, so I think it's 1.41. Let me double check that one there real quick. I think it's 1.41. Yeah. So what's peculiar with these numbers is they have decimals that go on forever, but another thing about them is these decimals that go on forever, there's no patterns. There's no sustained patterns, at least. And the reason we represent them using symbols, when you think about a rational number like 1/3, we represent it as 1/3. We represent it as 1 divided by 3. And if we keep dividing 1 by 3, we end up getting the 3 repeating. So we can represent rational numbers with, well, the way we get them. We represent them by the division of one number by another. 1 divided by 3, for example. The process is far more complicated, and so we just represent them with these kinds of symbols. Like, you get this one by taking the circumference of a circle and you divide it by the diameter. And as you keep working, if you keep trying to figure out the next digit as you do that division, you end up getting pi. At least in theory, that's what you're doing. It's a little more it's more complicated than that, but because you won't have a measurement, an exact measurement for the circumference without using pi as a symbol anyway. The stuff gets kind of complicated. This comes out of an idea of calculus that involves limits. And then this one, you can generate square roots by hand. It's actually really cool how you do that. But you can use the process of a way of doing this by hand. You'll just keep generating more digits as you go. So these are the irrational numbers. You get this when you're dealing with circles. This comes up when you're studying finance. Or excuse me, growth, like interest rates and stuff like this. This one just comes from geometry, really, is where it initially comes out. If you take a square that's 1 by 1, the length of the diagonal, that's the square root of 2. So these numbers, they come up, sometimes weird places, but they do come up. When we combine all these numbers together, we get the real numbers. It's the irrational with the rational. These are the real numbers. A way of thinking of it, you can draw a picture of this. You have your natural numbers. And then you have your whole numbers. The whole numbers are just the natural numbers, with the number 0. So the natural numbers are contained in the whole numbers. Whole numbers are contained in the integers. Integers are just whole numbers, but then with the added or included negative versions. If we take the ratios of the integers, we get the rational numbers. Integers are rational numbers. They're just rational numbers with a denominator of 1. And then everything that's not an integer, well, these will be rational numbers with denominators that aren't 1, like 2/3. Then over here, off to the side, you've got the irrational numbers, IRR, so we don't confuse it with the integers. And then finally, all of these together are the real numbers. Rationals and then the real numbers, and they combine like this. So if you say you have the rational numbers, you include everything that's on the inside, and then you have the irrationals. These together make up the real numbers. Questions about that? So there's something called set builder notation. So set builder notation is something like this. Let me rewrite this little part here. So the way this works, we treat X as a generic member of the group. And there's some fact that identifies this group. So let me make my parentheses a little bigger here. And then finally, this bar, this means such that. So this is very formal ways of describing groups of numbers. So for some number X, such that, well, these are the facts about X that make it a member of this set or a member of this group. So for example, let's take a look at even numbers. Let's make it a little more detail. Even positive numbers. So what we can do here is this. It's all numbers X such that, well, what would make X an even positive number? X has to be greater than 0. And X divided by 2 has no remainder. And so that's how we would describe positive even numbers using set builder notation. We're talking about a number x such that x is greater than 0 and x divided by 2 has no remainder. Let me check one thing. This is what I tend to forget. All right, there we go. Just want to double check. 0 is not considered positive. Just want to double check. I always forget that one. So for positive even numbers, x is greater than 0, x divided by 2 has no remainder. You might be wondering, it seems like a waste of time. Why just not say this right here? Why bother with this? Well, we could have something a little more complicated than numbers. Say the points on the line and so how you would write this as a set, all the points that are on this line, you could write it like this. X comma y such that x is a real number and y equals 2x. So sometimes you'll get a little fancy with this. If you're talking about points on the xy plane, you might say, well, a point on the xy plane looks like this. And x has to be a real number, something that you can get from the x-axis. And then to find the y-coordinate has to be twice x. Another way you could do this with even numbers. You go back to even numbers. You can describe, again, let's go with positive even numbers. We can describe positive even numbers like this. 2 times x such that x is a natural number and that'll do it. That'll give you positive even numbers because natural numbers are 1, 2, 3, 4. We don't have 0 in there. So if x is a natural number, it's already positive. It's already not 0. So 2 times 1, 2 times 2, 2 times 3, that's going to generate your even numbers. So you can get a little fancy with this. It's kind of cool. So that's set builder notation. All right. So in 1.1, another thing I'll mention, again, I'm not going to be able to cover everything just because of time constraints, but you think about intervals. So let's see what we have here. If you have something like this, this is the interval 2, 7. If you have something like this, on the number line, and usually this is shaded in. Sometimes it isn't, but usually it is. This would be 2, 7. something like this. 2 comma 7. And what's happening here, where we have parentheses, and sometimes some textbooks, instead of using parentheses, they'll use an open dot. This means we're not including the number 7. But a bracket means we are including the number 2. See, when I remember, brackets mean include, parentheses means don't include. And then that's going to look like this. We're including everything between and 2, and we're including 7. So that's the notation for intervals. Now, if we want to do something like with infinities, where it's 2 and everything above 2, we would do something like this. Include the number 2 and keep on going to infinity. And we never include infinity. I've actually seen one textbook that did do a bracket on infinity, and that's a whole other conversation. The reason is infinity, it's not a number, it's an idea. It means keep on going, don't stop. So we're going to start with 2. We're going to include 2. Let me emphasize, we're including 2. And then we're just going to keep on marching ahead, and we're not going to stop. If we have something like this with a parenthesis, and this could have been a bracket. I'm going to go with a parenthesis just for the sake of the example. But parenthesis means we're not including the number. So in this case, we're not going to include 7. And then in this particular example, we're going to keep on going into the negative numbers ultimately. So we're going to keep on going in the negative direction. And then that's how we would describe this interval. Questions about that? Let's see. So negative numbers. So negative numbers. Well, let's talk about their operations. First off, multiplication. For multiplying negative numbers, well, positive times positive is positive. Negative times negative comes out positive. So if they're both positive or both negative, you're going to get a positive answer. But negative times positive is negative. And then switch this around. And then positive times negative, that's also going to be negative. So when the signs match, you're going to get positive answers. When the signs are different, you'll get negative answers. Division. Same thing. same story. Same signs, positive answers. Different signs, negative answers. Now, adding and subtracting. First off, before we add and subtract, there's the double negative. This means minus -3 is +3, or just 3. You're usually going to be adding it, so keep it positive. Or if you see it like this, that's a +3, or depending on what you're doing, just 3. So we mean by double negative, we mean that. What we don't mean is something like this. This is not a double negative. This is what we mean by a double negative. The negative signs are literally one after the other. There might be a parenthesis, we'll allow that, but that's it. 2 negative numbers in a row, or negative numbers subtracting another number, we don't count that as the double negative. They literally have to be one after the other like that, the negative sign. So it's double negative signs, not double negative numbers. The other thing is we don't want to actually deal with subtraction. Subtraction equals adding a negative. So if we have 5 minus 3, we're going to turn this into 5 plus -3. Now, I mean, we know how to do this. We don't really have to. But something like this, though. We're going to rewrite this as -2 plus -7. We're going to do that. So we're going to convert all of our subtractions into additions. So we're still going to add numbers of different signs. -3 plus 7. First thing we're going to do, make everything positive. For this one, using the positive numbers, we'll subtract the smaller from the bigger. And we get a preliminary answer. Now we note, using the positives, that 7 is bigger than 3, and 7 was positive to start. So because 7 was positive to start, that means our answer is going to be positive. So 4 is just going to stay positive 4. Let me do another one. Any questions about this so far? I'll do another one with a little different twist. All right. So let's say we have 4 minus 8. Before we try to do any adding, let's take care of double negatives, turn our subtractions into addition. Now we can follow our process. Make everything positive if it's not positive already. Do our subtraction. Smaller number from bigger number. We get a preliminary answer. Looking at the positive numbers, 8 is bigger than 4, and 8 was negative. It started out negative. So because 8 started out negative, that means the answer will be negative. So 4 will become negative 4. Questions about that? So that's if they have different signs. If they have the same signs, we're adding two negatives. Remember, we want to do we convert all of our subtractions into additions, convert double negatives to positives, and then what we get left, that's what we're going to do. And so we have negative 3 plus negative 5. Same thing as before. To start, make everything positive. Instead of subtracting, though, we're going to add. And then finally, we attach to the answer, our preliminary answer, the common sign. Since negative, this will become negative 8. Because negative is the common sign. It's the sign that they share. And again, this only works for numbers of the same sign. Questions about that? All right. So another thing that comes up, absolute value. The absolute value of 3 is 3. The absolute value of negative 3 is also 3. Absolute value just gives you the distance of that number from 0. 3 is 3 units to the right of 0 on the number line. Negative 3 is 3 units to the left of 0 on the number line. Another way of thinking of absolute value, sort of a shortcut, make everything positive if it's not already positive. Opposite numbers. The opposite of 3 is negative 3. And the opposite of negative 3 is positive 3. So if there's some properties that are reviewed here, let's see. So I want to go through some of the properties. A plus its opposite is equal to 0. So for example, 5 plus negative 5 is 0. Also, you could do it this way. Negative 5 plus 5. They're opposites of each other. That's also going to be 0. There's a similar relationship with division or with multiplication. A times 1 over A is equal to 1. And this is for A not equal to 0. You want to be careful of divisions in 0. So in other words, 3 times 1/3 is equal to 1. Or you could do it this way. You could say 1/3 times 3. That's also equal to 1. Technically, what you have are reciprocals. Because you could think of this as 3 over 1. So 1 over 3 times 3 over 1 is 1. 3 over 1 times 1 over 3 is 1. So we can say this, and this is kind of a neat thing to help. 2/5 times its reciprocal, where we flip this fraction. Well, if we flip it, we get 5/2. That's going to be 1. Same thing for negatives. -3/2 times, and keep in mind here, we're going to keep the negative. Reciprocals have nothing to do with negatives. So we're going to keep the negative. We're just going to flip things. That's all we do with reciprocals. We just flip. Well, negative times negative is positive. And 3/2 times 2/3, those are reciprocals. Again, it's going to be +1. So any number divided by 0 is undefined, including 0. If you have 0 divided by 0, that's also undefined. But 0 divided by, say, any number is 0, provided, again, we're not dividing by 0. So anything divided by 0 is undefined. 0 divided by 0 is undefined. But 0 divided by any number that isn't 0, that's going to give you 0. So the associative property, this means grouping doesn't matter. This is only true for multiplication and addition. It's not true for subtraction and division. So what does this mean? Well, 4 plus 2 plus 8 equals 4 plus 2 plus 8. We could do these two first, or we could add these two first. We're going to get the same answer no matter what. Commutative. Commutative is the order doesn't matter. So again, only for multiplication and addition, not for subtraction and division. It's for this and not for that. So for example, 2 times 4 times 8, well, this will be the same as 2 times 4, and then times 8. Oh, I'm sorry, that's associative. What am I doing? I'm sorry. We're talking commutative. So commutative would say 2 times 8 is equal to 8 times 2. So that's your commutative property. It's checking the time. All right. Ooh, what? Distributive. A times B plus C. What we're going to do, we want to get rid of parentheses. That's the idea of the distributive property. So we can take A times B plus C, multiply B by A, multiply C by A. We'll get A times B plus A times C. And that's going to be how we handle distribution. So for example, you want to get rid of the parentheses. We can distribute. We'll get 5x plus 15. And that will let us get rid of the parentheses. So order of operations. Again, this is PEMDAS, parentheses first, exponents, multiplication, division, and again, left to right, and then addition and subtraction, again, left to right. So there's basically 4 stages: parentheses stage, exponent stage, multiplication division stage, addition subtraction stage. And we're headed in this direction. We start with parentheses, we finish with addition and subtraction. So let's say we've got something like this. Let's see. So following PEMDAS, we want to do any operations in parentheses first. So you have 6 plus 2, this will be 8. Next, we want to do exponents. So we have 8 squared and 2 squared. Next, we're going to do multiplication and division. And we're going to go from left to right. So starting here and moving over, we first get 16 divided by 4. And then the next thing, once we take care of this division, we're going to deal with the multiplication. That's 4 times 4 is 16. Now we do subtraction going left to right. We've got a subtraction. What's that going to be? 54, 48. And then 48 minus 3 is going to be 45. All right. So that's how we can do the order of operations. Now, a particular order of operations, any questions so far? So a particular order of operations if you have something like this, whew, yikes. We want to treat this as a division. So we can think of this as having parentheses. And that would be treated as a division. So we're going to come up with a number here, come up with a number here, and once we've got those two numbers, we'll do this division last. So taking a look, we got to do what's inside here first on the bottom part. In this part, we got to do the exponent first. This one we'll get. And we might want to do this, but we can't do anything with this exponent until we finish what's in the brackets or parentheses on the inside. So technically, on the bottom part, we've got it. We're still on the P here. And then once we get this into a number, then we can move on to the exponent. Now on the top, we have multiplication or subtraction. Multiplication is going to be first. So we'll get 10 minus 9. At least it's before subtraction. Now we're still digging in here. Now here, we've got a double negative. So this will be 9 plus 2 squared. Now on the top, we can just do the subtraction. On the bottom here, we still got to work within the brackets. So this will be 11 squared. And then finally, we can do the exponent on the bottom. We'll get 1 over 121. And since 1 isn't divisible by 121, we can leave it as a fraction. 1 divided by 121, or the fraction 1 over 121. Think of it either way. So solving equations for x. Let's see. Let's solve one for y. So we've got something like this. We've got parentheses. We want to get rid of parentheses. The only way we can do that is distribute. And when we distribute, make sure to bring the sign. If it's a positive sign, you don't got to really worry about it. But if there's a negative, bring that negative sign. So what this will give us, 9y minus 18 plus 15y will be y minus 6y minus 18. Negative 2 times 9 is negative 18. We then want to gather like terms. So there's a 9y and a 15y over here. We'll combine those. We have 1y and negative, oh, sorry, that's negative 18. That's all right. And then there's a negative 6y over here. And again, I'm going to include that sign. So 9 plus 15, 24y. Still keep that negative 18 there. 1y subtracts 6y. Or another way of putting it, 1 minus 6. That comes out to negative 5. And we still have a minus 18 over here. So what we could do, we could add 18 to both sides. We'll get 24y. Negative and positive 18 is 0. Negative 18 and positive 18 is 0. Negative 5y. Add 5y to both sides. So that'll cancel. Divide both sides by 29. 29 will cancel here. And then 0 divided by a non-zero number, that's always 0. And that's going to be our answer. Questions about that? Oh, great. So working with formulas, solving for a variable. So let's say we're going to solve for D1. What I recommend is let's get rid of fractions. That's always a good idea. And one way we could do that here is cross multiply. Let's call this V over 1. If we cross multiply, we'll go V times D. And then 1 times D1 minus D2. So get V times T, and then 1 times D1 minus D2. Or VT is D1 minus D2. Because 1 times this Doesn't change anything. Multiply by 1, nothing changes. So this is d1 minus d2. Now we're solving for d1, so we're going to treat it like it's the only variable and everything else were numbers. So to get d1 by itself, we got to cancel d2. We'll add d2 to this side. Now what's vt plus d2? I don't know. So I'm just going to leave it as vt plus d2. And I'll wait for someone to come along who can replace these with numbers and make sense of all this. But that's the best we can do, and that's going to be our answer. Questions about that? Now, we're going to be running out of time, so what I'm going to do, I'm going to go long. If you need to go someplace, go ahead. I'm recording this, so I'm going to post it up on YouTube. I'll send out the link, and I'll send it out immediately, actually, once I finish recording. And then, or as soon as I can, once the recording's ready. So I'm going to keep going, doing some examples, at least from chapter 1, because I know it's been a while since we've done chapter 1, and there's a lot of material in this chapter. Chapter 2, to a large degree, I'm going to kind of leave up to you just because we've done it recently. But if there's a few problems, I might pick from chapter 2 also. But I'm going to keep going. If you need to go someplace, go ahead, because I know we're coming to the end of the time. But I'm just going to keep going. And if you want to see what you had to miss, don't worry. I'm recording it. It's going up on YouTube. So I'm just going to keep going. And again, the review, it's not comprehensive. It's just there to help you get an idea, just kind of give you a head start, give you a little bit of a kickstart. So that means I want to do one of these problems. I want to back up a little bit, because I think this is one that kind of gives everybody a little bit of a headache. I like them, though. It's this. Let's see. I'm going to change some numbers here just to make sure we haven't done this one already. And let's do this. Ooh, do I really live to regret this? A little bit. So the thing with this, to solve for x, get rid of denominators. And so you want to find some number that 5, 4, and 3 divide into. There's a number that's divisible by 5. That means there's no remainder. That same number is divisible by 4, no remainder. Same number is divisible by 3 with no remainder. So what is this magical number? What does all this? Well, there's a number of ways of doing this. You don't have to find the lowest number. The easy way to do this is just take these 3, multiply them together. And sure enough, 60 is going to be divisible by 5. I mean, we multiplied it in there. Turns out it's 12. 60 will be divisible by 4. It's going to be 15. And 60 divisible by 3 is going to be 20. So we don't get any remainders. They all divide in evenly, which is nice. So we could use 60. Now, another way of doing this, we're going to try to come up with what's called the lowest common multiple. We can list out the factors of 5. It's really just 5. The factors of 4. Well, that's 2 times 2. Remember, factors are prime numbers that we can multiply together to get our composite number. And then 3, well, that's just 3. We don't really count 3 times 1. So now we want to try to make these lists of prime numbers, because 5 is prime, 3 is prime, and 2 is prime. I want to make these look the same. So what's this list missing? Well, it's missing 2 2s. Better bring in some 2s. And it's also missing a 3. Better bring in a 3. Now what's this list missing? Well, it's missing the 5 and it's missing a 3. And then what's this list missing? Well, it's missing a couple of 2s. It's missing a 5. So, and this is sort of a longer way of doing it, I'll admit. But if we multiply these together, we're going to get our lowest common multiple. And it turns out it's going to be 60. It'll be 60 for all 3 of these lists because these lists are products of all the same prime numbers. So however method we choose to do this, and this is having the multiple lists is just a good way of checking, because if you get different numbers here, something's gone wrong. You want to be careful of that. So no matter what method we used, we get 60. So what do we do with 60? Well, what we're going to do is multiply 60 throughout this equation. So we'll get 60 times 3x over 5 minus 60 times, I'm going to put this in parentheses because we're multiplying the entire top part, x minus 4 over 4, and then 60 times x plus 7 over 3. So once we figured out 60, that's what we want to do with 60. Now here's the clever part. Remember, 60 is divisible by 5, divisible by 4, and divisible by 3. So that means 5 goes into 60 12 times. Our 5 is gone. 4 goes into 60 15 times. The 4 is now gone. 3 goes into 60 20 times. And now the 3 is gone. And we've done what we wanted to do. No more fractions. Now we're on familiar territory. Let's do some simplifications. We want to get rid of these parentheses. We do that by distributing. Now 12 times 3 is 36. Again, we're going to distribute the sign. We'll get minus 15x. Now minus times minus will be positive. That'll be plus 60. 15 times 4 is going to be 60. Equals 20 times x is 20x. 20 times 7, 140. Now on this side, we can combine like terms. 36 minus 15, 21x. And 20x plus 140. So I'm going to get the x terms on one side. I'll cancel the 20x here. Do it over here too. 21x minus 20x leaves you one single x. And we always write one x as just x. And then subtract 60. X is 80. And that's going to be our final answer. So we want to get rid of fractions wherever we can. Like in the formula example, we use cross multiplication. In this example, we come up with a common multiple, or a least common multiple. It doesn't have to be a least common multiple though. Just a common multiple is good enough. That'll be fine. So with the exponents, I'm going to let you review the properties on exponents, but I want to do some gnarly problem, a couple gnarly problems for the review. So in fact, let me do one gnarly problem, real good one. Let's see. Ooh, that's a good one. So what we want to do here, first off, we're going to distribute our exponents. So this will go here, here, we're going to distribute here. And exponents are actually going to exponent. So when I point to the 2, this is not -1 times 2. No way. This is going to be -1 as an exponent of 2. -3 as an exponent of x. -3 as an exponent of 4. Now, technically what's going on, you have 2, well, anything by itself. This is really 2 to the 1. And so what we're going to end up getting with this distribution is 2 to the 1 times -1, which will give us 2 to the -1. Same thing with this x. X, it's really x to the first. And when we distribute this -3, it'll be x to the first times -3, or x to the -3. So you want to be careful here. It's not -1 times 2. No way. It's actually 2 to the first power getting -1 as an exponent distributed. So where does this get us? We'll have 2 to the -1. 2, this 2 times -1 is -2. And 4 times -1 is -4. Times this whole piece, 4 to the -3, x to the -3, y to the -9. X, 2 times -5 is -10. Y to the -5 times x to the 12, and then x to the 8. So questions about distributing our exponents. This is what we call the, I think it's the product of powers rule. Let me double check that name. Or the power rule, it's just called the power rule, I'm sorry, power rule. And also product of powers also, we use both of those at the same time. So now we're going to try to combine things. We got this 2 to the minus 1 times 4 to the minus 3. X, this will be x to negative 2 plus negative 3. When we multiply variables like this, we add their exponents. Same thing for y. Negative 4 plus negative 9. Down here, we'll have x to the negative 10 plus 12, and then y to the negative 5. Ooh, I'm missing something. Let me check. I think I miswrote something. This is y to the 8th. I'm sorry. Y to the 8th. Ooh. Ooh, that changes things a bit. Plus 8. So that's y to the 8th. So now we simplify things. Two to the minus 1, 4 to the minus 3. This will be x to the negative 5, y to the negative 13, x squared, y cubed. So what we do here, we want to get rid of negative exponents. So the way we do that, one way of thinking of it, if something has a negative exponent, the way you get rid of the negative exponent is drop that thing down. And that allows you to get rid of the negative exponents. And then this, we still have the x squared y cubed. It stays on the bottom because they don't have negative exponents. If they did have negative exponents, they would pop up. Now, when we get a blank like this, we always want to insert a 1, just like we do when we simplify fractions or reduce fractions. So what we'll get. Now 4 to the 3rd, 16, 64. This is 2 times 64. And again, we have x to the 5 plus 2, y to the 13 plus 3, and then this will come out to 2 times 64 is 128. X to the 7th, y to the 16th. And that's going to be your answer. Questions about that? So remember, with negative exponents, if they're in the numerator, you get rid of the negative sign by dropping them into the denominator. If they're negative in the denominator, get rid of the negative sign by bringing them up to the numerator. So the things in scientific notation I'm going to go over. So there's a couple things I want to look at. So for large numbers, to put large numbers in the scientific notation, you're going to move your decimal point to the left. And you move it to the left until you get a number between 1 and 10. It could equal 1, but it's got to be less than 10. And there's 4 jumps. So that means we get times 10 to the 4th. So that's how we put large numbers into scientific notation. To move them out of scientific notation, we're going to move to the right with the decimal. So this 3 tells us how many jumps we need to make. We fill in the zeros. So for large numbers, that's how we deal with scientific notation. Now, what about small numbers? So for small numbers, it's all going to be reversed. Do this. This is fun. So to go into scientific notation, instead of going to the left, we're now going to go to the right. And this is for small numbers. And we go right until we get a number between 1 and 10. It could equal 1, but it's got to be less than 10. So we have 4 jumps. And for small numbers, what we're going to get is 5 times 10. And for small numbers, a negative exponent, 5 times 10 to the negative 4. That's what you get for the small numbers. Now, for small numbers leaving scientific notation, well, in this case, we're going to go to the left. So we'll have 3. So 1, 2, 3, 4, 5. And that's where we'll put our decimal. So negative 5 is the exponent. 5 jumps to the left. And that's going to be our answer. Now, something that can come up sometimes you can do something with numbers in scientific notation. And if you do some multiplications of those numbers or divisions of those numbers, you might end up with something like this. For example, let's say you get 121 times 10 to the 6th. This is not technically scientific notation. And the reason it's not, it's this thing. We need a number between 1 and 10. This is way bigger than 10. So here's a trick we can do. We can turn this into scientific notation itself. So it's a big number. In other words, it's not a little decimal number. So to put that in the scientific notation, we move the decimal to the left, and that's going to give us because we have 2 jumps. So now what we're going to do, this will be 1.21 times 10 squared times 10 to the 6th. And just like with x, like x squared times x to the 6th, it's x to the 2 plus 6. Same thing here. 1.21 times 10 to the 8. So you could think of it like this. This is kind of a hard way. You could also think of it as we're converting a number into scientific notation, and we just need to go 2 more jumps. And for large numbers, that increases this by 2 more. So you can think of it like that also. It's a faster way to do it. For a tiny number, if you have something like again, it's not scientific notation because we need this between 0 and 1. So we're below 1. So what you can do, you can think of this we need to go 2 jumps right because this is a small number. And so we get 3 times 10 to the negative 2. So this means we have 3 times 10 to the negative 2 times 10 to the negative 17, which will be 3 times 10. We're going to add these exponents to the negative 19. Or if you want to think it faster, you could think of this as if we were converting this number into scientific notation, and we're just 2 steps short. So we go 1, 2 more, we'll add negative 2 to this, and then that'll give us negative 19. So you can think of it either way. So I'm going to jump into some chapter 2 here. So things that could come up in chapter 2, is something a function or no? So here's a set of points. Here's another set of points. So which one of these is a function? Well, what we want to look for are repeated input values. So when we talk about points, points are called ordered pairs. That means the order of the numbers matters. And what matters about them is the first number is always the input. The second number is the output of some process. Pardon me. So for example, let's say you work 3 hours and the payment for 3 hours is, say they're paying you really well, 6 $10 bills. So you input 3 hours, you get 6 $10 bills. So the thing you want to be cautious of is what's called ambiguity. So if you work for 3 hours, you want to know if you're going to get $6 bills, $10 bills, or if you work for 3 hours and get 7 $10 bills. Well, which is it? Do I get the 6 $10 bills or the 7 $10 bills? That's ambiguity. And that means that's not a function. And this you can identify when you have input values repeated. So this would be not a function. Now this one here, there's the input, 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 input. They're all different. So that means this is a function. Now, it might not be a fair function, though. For example, this person would work 4 hours and get 2 $10 bills. This person will work 8 hours and get 2 $10 bills. What the heck? Well, this person here could be per the entire 2 hours, the entire 4 hours is carrying heavy steel beams. And let's not call it $10 bills. Let's move it up here. $100 bills. 2 $100 bills. 2 $100 bills. This person's carrying steel beams and doing Pythagorean trigonometry with right triangles in their head at the same time. So for the amount of time they're working, we're going to pay them pretty well. This person here is me. I'm sitting at my desk playing solitaire because nothing ever happens. I'm just sort of there to, I don't know, let somebody know when lunch arrives. I'm not working, I'm doing something. I mean, I have to be there, but I'm not working very hard. So for my 8 hours, I get 2 $100 bills. So the point is this. Ambiguity is what we don't want. Maybe you might consider it unfair, like 4 hours, 8 hours, same amount of pay, but unfairness isn't an issue. Though I kind of think the way we described it, that does seem kind of fair. But it's ambiguity we don't like. If I put in 3 hours, I want to know how much I'm getting paid. Or am I getting paid that? Ooh. But in this situation, if I work 4, I know what I'm getting paid. If I work 8, I know what I'm getting paid, whether I like it or not. But I do know. It's when we're not sure how much we're going to get for our effort. That's when we're not a function. So function notation, just to kind of review what this is. So f of x so when we say f of 5, this means we're replacing x with 5. So everywhere we see an x, we're going to replace it with 5. So remember, this is 3 times x squared. So we have 3 times 5 squared plus 4 times 5 minus 2. Or, and again, we're going to follow the order of operations. Exponents first. There aren't any calculations in parentheses. The numbers in parentheses just mean multiplication. They're just numbers. There's no calculations we need to do. So we can move on to exponents. So 3 times 25 plus 4 times 5 minus 2. Now we can move on to division and multiplication. There's a multiplication. This will be 75 plus 4 times 5 minus 2. There's the other multiplication. Now we can move on to addition and subtraction. And again, we process it from left to right. So here's one. And then finally we get 93. That's going to be our answer. Questions about that? So graphing functions. Again, we want to come up with an inputs column that we'll call x. And an output column we'll call f of x. And we'll have a formula for how to calculate or come up with the output. So what this says is that whatever input we choose, and since we get to choose it, we refer to this as the independent variable. We're going to come up with an output by multiplying the input by 3. And then we'll add 1. And that will give us our output. When this is a y, we call it the dependent variable because its value depends upon the choice of x that we made. I'm just going to pick 3. -1, 0, and 1. F of -1, 3 times -1 plus 1. And that comes out to -2. F of 0. This will be 0 plus 1 will just be 1. F of 1. And that's going to be 4. So the ordered pairs you're going to get we input -1, we get a -2. We input 0, we get an output of 1. We input 1, we get an output of 4. Now we're going to graph this. So when we have an input of -1, we get an output of -2. Now there's different ways you can think about graphing. You can always, one way I haven't really talked about is you start at the origin, input -1. So we walk out along this axis to -1. Then the output is -2. So we drop down to -2 and we put our point. Now the way I've been showing you is when inputs are vertical lines, outputs are horizontal lines. And where they intersect is where you put your point. Either method will work. I'll use both for this. So now we have an input of 0 and an output of 1. So I could put a vertical line for the input 0, and then a horizontal line for the output of 1. And I get a dot. Or the other way you can think about it is I start here and I go to x is 0. I'm already at x is 0. Oh well. Now I go up to f of x is 1. So that means I go up here and then place my dot. So we could think of it like that. Finally, we have an input of 1. Again, inputs are vertical lines. We have an output of 4. So outputs are horizontal lines where they cross as we put a dot. Now, another way you could think of this, if you wanted to, is you start here at the origin. Input is 1, so march out to 1. And now the output is 4, so I march up to 4 and then put a dot. Either approach will work. And then we connect these going left to right. Left, then the next point is going to be this one, so we connect. The next point going over will be this one. And that's going to give us our graph. Questions about that? So next, algebra functions. So f of x equals x squared. G of x is x plus 2. So f plus g of x will be f of x plus g of x, or x squared for f of x, plus, and now for g of x, x plus 2. And these don't simplify any further, so we're done. Now this one, f minus g of x will be f of x minus g of x, or x squared minus x plus 2. And we want to distribute this minus sign. So we get x squared minus x minus 2. Questions about that? F times g of x is f of x times g of x, or x squared, which is f of x, times g of x. This is x plus 2. This is the entire g of x. So we got to distribute f of x. And not just the exponent, but the whole thing. So we're going to get x cubed plus 2 x squared. Because this is an x to the 1. Again, if there's no exponent there, there's an invisible 1 as an exponent. So you're going to add the exponents. 2 plus 1 gives you 3. Finally, let's check one thing. I don't think they actually had you do compositions. No, not yet. So f divided by g of x. Well, this will be f of x divided by g of x, or x squared, or x plus 2. Now, a common question to ask about functions is going to be the domain. And for us, we want to look for domain in 3 situations. There's certain numbers we want to avoid. We want to avoid numbers that cause division by 0. We also want to avoid numbers that cause the square root of a negative. And then finally, there's certain numbers Let me put a star on this because there's certain special numbers we might not be allowed to use. The common one, again, is time. When we're doing a function or using a function that involves time, we usually insist that the inputs are 0 or greater. We don't use negative inputs if we're talking about time as an input, usually. And so we might have a domain that says all our numbers have to be greater than or equal to 0. So there's certain special numbers we're not allowed to use. We want to avoid the square root of negatives. We want to avoid division by 0. So let's take a look at this function. Let's say we're asked to find the domain of this function. Well, the problem, so to speak, that I gave us doesn't mention any restrictions on special numbers. So we don't have to worry about this. Taking a look at this, there aren't any square roots. So we're okay there. But we do have division. And it could be possible that this thing here could become 0. So if this were to become 0, what number is going to cause it to happen? So if x plus 2 became 0, well, what does that? What value of x we got to avoid? Let's solve for it. 0 minus 2 is actually -2. So the number we want to avoid is x equals -2. So now we know which number we want to avoid. So that number cannot be in our domain. So we could write an answer that says all real numbers except -2. That would be our domain. And we tend to do this symbolically. So symbolically, here's number 2 on our number line. And what's going to happen? We're going to put a hole here. We can't have -2. So we get everything to the left of -2 and everything to the right. Well, how do we describe everything to the right? Well, we don't include -2, but we can keep on going to the right using those numbers. That's fine. To the left of -2, well, we can't have -2, but we can keep going into the negative numbers into the left. And so these are the numbers we get to use to the right of -2. These are the numbers to the left of -2. And the way we actually write this up or input it, put a union here. We'll take these numbers, dump them into a box, take these numbers, dump them into a box. We put them together, we union them. And that's going to be your answer. Questions about that? All right. So getting into lines, there are 3 equations for lines. There's the standard form, ax plus by equals c. This is standard. There's y equals mx plus b, and this is slope-intercept. And then finally, there's this one, which is point slope. So lines, one of the things we might be asked to do, with a graph of line, we just need 2 points. So the 2 points that are commonly used are the intercepts, the x and y intercepts. So let's say I have a line in standard form, and I'm asked to graph this line. Now, there's different ways we could do this. Like I could solve for y, put this in y in slope-intercept form, and then graph using slope-intercept form. But I can also just use intercepts. So using the intercepts, to find the x-intercept, let y be 0, and then we'll solve for x. Well, I'm going to circle this. I mean, technically, this is the x-intercept, but the full x-intercept is the point. So you get xy is going to be 8/3, 0. That's really going to be your x-intercept. Y-intercept. Here we let x be 0. So we'll get 3 times 0 plus 2y is equal to 8. This zeroes out. And 2y is equal to 8, or y is equal to 4. So the y-intercept is 0, 4. And if we plot the y-intercept and the x-intercept on the xy plane, that's enough to graph. That's all we need to graph. Grab another pen real quick. So again, any questions? They can out of pins. We'll make it work. So we want to talk about slope. Slope is rise over run. And again, rise, if it's less than 0, is a fall. You're going to drop down. So if the rise is less than 0, it's really a fall. You're going to drop down. The other thing to keep in mind with run, I mean, you can devise a different way of looking at it, but it's almost always viewed as left to right. And for that reason, if there's a negative sign on the run, move it up to the rise. And make the rise negative, which means you're going to drop down. So a formula for this, if we have 2 points, if we just have 2 points, to find the slope between those 2 points, we're going to use this formula, where this 1 signifies the first point, the 2 signifies the second point. So these are our 2 points. And let's say we want to find the slope between those points. So what I recommend is, if this is our first point, let's label it x1, y1. This is our second point, call it x2, y2. And then we're just going to plug things in. And again with slope, what I'm going to recommend is move the negative, or you can just move it out in front if you want to. But if you're going to actually graph using the slope, move it up to the top. Don't leave the negative down in the bottom. Move it to the top or move it in front. Or if you're going to graph using the slope, you got to move it from in front, then move it to the top. And this will reduce down to -1/2. See, I'm going to put it in the top there. So let's say I want to graph this line. How could I do that? Well, I know the slope's -1/2, and this is x1, y1. Now let's say I don't know the second one. Let's say the slope is -1/2. And let's say I'm going to graph this line. Well, I have an x1 and a y1. I need an x2 and a y2. So what I can do, first off, I'm going to change the slope. I'll put my negative up on there. So now my rise is -1. My run is +2. And that means this is going to be a fall. So to come up with x2 is x1 plus the run, or 7 plus, and the run's going to be the bottom number 2, or 9. y2 will be y1 plus the rise, or 2 plus -1, or we get +1. So for our x2, y2, we're going to get 9 and 1. Now we can graph this thing. To do very qualitative graph. So this is 7, this is 9, here's 1, here's 2. So 7 and 2 is about here, 9 and 1's about here. And we can graph like that. And then there's an 8 in between. So that's one way of doing this. So slope-intercept form. Here's the slope. It's equal to 3. Or we want to make sure it's 3 over run. So this is our rise. This is our run. I'm going to break things open like that. This here is the y-intercept. And it's 0, 1. So the way we can graph this we have a y-intercept of 0, 1. So that puts us right here. We need to generate a second point. So this here is our x1 and there's our y1. So we can generate x2, which will be x1 plus the run. That's going to be 1. And then y2, which will be y1 plus the rise, which will be 4. So the next point would be 1 and 4. Now let me show you a quick trick though. Instead of doing the calculation here off to the side, using those two formulas, we start at 0, 1. We run 1, and then we rise 3. So again, run's always left to right in this scheme. So we run 1, and then we rise 3. Well, there we go. So you could think of it like this too. We start at 0, 1, and then run 1, and then rise 3, and then put your point there. Either method will work. So any questions about that? All right. So the one I want to get into next is the point slope formula. And a really good example, I mean a really good example to know on this one, is if you're just given 2 points. Let's say you want to find the equation of the line that passes through these 2 points. Now, the way the point slope formula works is if you're given a slope and a point, you can find the equation of the line. Now, we have some points to work with, but they didn't give us a slope. They don't have to. As long as they give us 2 points on the line, we can find the slope. So again, I'm going to label these x1, y1, x2, y2. Calculate the slope. So again, 5 minus 2 over 5 minus 3, we'll get 3 halves. So that's going to be our slope. Now we can plug this into here. And I can use this for x1 and this for y1. That's perfectly fine. I could also do this. I could use x2 and y2. And again, the reason you'd want to probably use maybe one point over the other, say one point has fractions and the other point doesn't. That just makes life easier to use the point that doesn't have fractions. Sometimes. So we'll get, I'm going to stick with the schema we have, y minus y1, that's 2. And then the slope, 3 halves. X minus x1, which is 3. So we get y minus 2. Distribute the 3 halves, we get 3 halves x minus 3 halves times 3. We want to think in terms of fraction multiplication. 3 over 1. We get y minus 2 is 3 halves x minus 3 times 3 is 9. 2 times 1 is 2. We can add 2 to both sides. We need a common denominator to add fractions. We could think of this as 2 over 1, because 2 is equal to 2 over 1. And to turn this into that, that's how we get our common denominator, multiply by 2. And remember, we can only use multiplication by 2 or division to change these bottom numbers to get common denominators. You only use multiplication and division. We can always multiply by something other than 2. But what we do have to follow is this rule. We also have to do this. What we do to the bottom, we've got to do to the top. Now we can think of this. I'm just going to put a plus sign here just because pluses are kind of harmless. I'm going to think of this as -9 plus 4. Or if I want to be more accurate, remember we want to turn subtractions into adding a negative. Or more complete, I guess you could say. Now I can do my adding fractions. So now we're good to go. So if I convert my subtractions into adding a negative, it makes a lot of things just easier. -9 plus 4 is -5/2. And now we're adding a negative. Now let's bring it back into subtraction. And because this is an x term and this is a constant term, we can't combine them. That's going to be our answer. Questions about that? All right. So last couple questions I want to do, and then I'll call it for today. Let's say you have this line. Let's say you have to find a parallel line. Well, for a parallel line, it's any line with the same slope. So the slope here is m is 1/2. So any line with a slope of 1/2 will work. So let's just kind of do it easy. 1/2 x. And if you want to pick a y-intercept, you can, like +1, -4. It's probably a good idea to pick one different from this y-intercept, because what they're probably implying with this question, or what they might say, you might skip over it, find a different line that's parallel. So this is definitely a different line, because it doesn't have a y-intercept, or it has a y-intercept of 0. Perpendicular. Now again, The slope we have been given is 1/2. There's a formula for the perpendicular slope. Now this means perpendicular. It's minus 1 over the slope we're working with. So you got to divide 1 by 1/2. -1 divided by 1/2 is -2. So that's the perpendicular slope. So any line with this slope will be perpendicular to that line. So again, we could go simple. Y equals -2x. And that's it. So that's the review. It's not everything. There are some problems we didn't cover, but it gives you kind of a start. It gives you kind of an idea, just kind of a kickstart into what to do, and continue on. It's basically what I would say. If you have problems that you've seen today, they're like, gosh, I don't know about that one. Go do some practice problems on that, particularly examples in the text where it gives explanations on what to do. And then also go through the text. There are some problems we didn't cover, like we didn't do any story problems. We didn't graph any parabolas. So there are some things you want to go through and make sure those make sense. But that's it. If you have any questions, let me know. And then I'll get that test information sent out as soon as possible. Other than that,
I have a question.
Oh, I'm sorry?
I have a question.
Yes, what question?
Do you know how many questions will be on the test?
I'm not sure. It's for the online class, it might be a department test. So I need to contact the department to find out. It's usually between 20 and 30 for the first test. I think it's between 20 and 30. And there were some problems I did today that were pretty hard. I don't think you're going to find some. There were some that I don't think you would see on the test just because they were somewhat difficult. They have to make a test because it's a time test. They have to make it reasonable so you can finish it on time.
And it's going to be timed, correct?
Correct. It will be timed.
Okay. Okay, thank you.
No problem. Did this help? Oh, no, never mind. I'll find out later. Have a wonderful day.
It did help a lot.
Okay, good. I was hoping it did some.
Thank you. You too. Have a good day.
No problem. Have a good evening, Priscilla.
You too. Thank you.
No worries.